here's the main relationship or example of a relationship between logarithms and exponentials that I like to remind myself of all the time. 2 to the third is equal to 8. No big deal. This is equivalent to, or has the same meaning as, you often use this double-sided arrow to mean equivalent to, log base 2 of 8 is equal to 3. So these two equations are really the same equation, just written in different ways. And so here's what I really want to make sure everybody understands. And I'm going to make some parallels to something we did before. So when I see the phrase or the expression log base 2 of 8 should be read as, or is read as, and this is going to be very similar to when we talked about inverse trig functions, because it's actually the same kind of idea. So the way I want you to read this is the exponent, or power if you prefer the word power, the exponent to which we raise the base 2 to get 8. So when I see log base 2 of 8, the words I hear in my head are 2 to what power equals 8. So when I see this, I think this. 2 to the what equals 8. And the answer, which is the exponent, is 3. So that's why you might hear people say a logarithm is an exponent, because really they literally mean the logarithm is the exponent that you raise this base to get this number. You see that all right, Lindsay? In a similar way, so we could say the same sort of thing about log base 3 of 81. This means 3 to the what equals 81. And the answer is 4. We know 3 to the 4th equals 81. So we know that log base 3 of 81 is equal to 4. It is in fact very, very similar to how we talked about the inverse trig functions. So I want to kind of remind you guys, I need to erase some stuff because I need the other side of the board. So this is right here. So I kind of want to draw a parallel for everybody. So this is just like how the inverse trig functions worked. Before we had sine of pi over 6 is equal to 1/2. And inverse sine of pi of 1/2 is equal to pi over 6. I'm going to remind you that the words we said for inverse sine of 1/2 were, right? Inverse sine of 1/2 is the angle whose sine of that angle is 1/2. And the angle that we're looking for is pi over 6. In the same sort of way, we have the following relationship. 5 to the 3rd equals 125. Or equivalently, log base 5 of 125 is equal to 3. Because log base 5 of 125, this is the exponent that if we raise 5 to that power, 5 is the base, we get 125. So what power do we raise 5 to get 125? Oh yeah, the power is 3. 5 to the third equals 125. So it is literally the same sort of thing because a logarithm is the inverse relationship of an exponential, right? You're interchanging the role of the input and the output, just like with the sine and the inverse sine function. For the sine function, you're inputting pi over 6 and you're getting out a value of 1/2. For the inverse sine function, you're inputting the value of 1/2 and you're getting out the value of pi over 6. The same sort of thing is true here. If you think of this as being the function f of x equal to 5 to the x, you're inputting a value of 3 and you're getting out a value of 125. If you think of this as being f of x equal to log base 5 of x, you're inputting 125 and you're getting out 3. So you're inverting or interchanging the role of x and y.
I have a quick question.
Go right ahead.
Right there where it says the angle whose sine of that angle, what does that next bit say?
So I was being maybe overly repetitive there. But
Yeah.
So it says the angle whose sine, meaning the angle that if you take sine of that angle, which is all we're writing right here, is equal to 1/2. Sorry, maybe this part, maybe this. So let me see, write that again. The angle whose sine is equal to 1/2.
Thank you.
But yeah, I was maybe being overly wordy there. I'm sure I've never been accused of. I'm kidding. I'm sure I'm quite often overly wordy. Okay, so now I want to, really what I want to do for you guys, what I want you to see or be able to do mostly is graph these things. There are definitely other properties of logarithms that you should know, will learn, depending on what you take next quarter. But mostly I want you to know about the graphs. Although I really want you to know all the things about logarithms, but we only have time to talk about the graphs. So let me show you some graphs. And I already graphed them because I was bored. So here's our graph of 2 to the x with the usual values. I've plugged in, right? In fact, we can even make a little chart just in case you can't see the values here very well, right? X could be -1, 0, 1, 2, or 3. And y is 2 to the -1, which is 1/2, 2 to the 0, which is 1, 2 to the first, which is 2, 2 squared, which is 4, 2 cubed, which is 8. And so I've got these pairs, right? I've got -1, 1/2, I've got 0, 1, I've got 1, 2, I've got 2, 4, and I've got 3, 8. Now, just like I was saying before, how the x and the y's interchange, literally all I did was I interchanged every pair of x and y to get these points over here. Instead of -1, 1/2, I have 1/2 -1. Instead of 0, 1, I have 1, 0. Instead of 1, 2, I have 2, 1. Instead of 2, 4, I have 4, 2. Instead of 3, 8, I have 8, 3. And that's because if you're taking log base 2 of x, well, I think I can, yeah, let me just, no, I'll try and fit it in here. So if x is, so again, picking the x values, let's start with the biggest one. If x is 8, y is going to be log base 2 of 8. But again, when I read log base 2 of 8, I'm saying 2 raised to what power equals 8? Oh, 2 to the third power equals 8. And if x is 4, log base 2 of 4, well, 2 to what power equals 4? 2 to the second power equals 4. Do be careful. Sometimes people confuse raising to a power with multiplication. And this is an example where it could kind of work either way, like because 2 to the second is 4, but 2 times 2 is also 4. But just remember, this one has to be like this, right? 2 to the third equals 8. 2 times 3 doesn't equal 8, it equals 6. And then if it's a 2 here, log base 2 of 2, you're just saying 2 to what power equals 2? Oh, 2 to the first power equals 2. And then if x is 1, log base 2 of 1, you're saying 2 to what power equals 1? Well, anything to the 0th power equals 1. So it's got to be 2 to the 0th power equals 1. And finally, if x is 1/2, log base 2 of 1/2, 2 to what power equals 1/2? Oh, it's the negative 1 power, right? 2 to the negative first is 1/2. So that's how we're getting, well, I mean, it's one of the ways we're getting all these coordinates. You can also see it literally by just taking the flip or interchanging all the x's and y's. I'll say that later. Yeah, so let's excuse me, let's talk a little more generally. But I will say, and what I'm about to say here is that, so just like last time when we talked about exponential graphs, and we saw that they basically all have the same shape that goes, up from left to right. Logarithms are also all going to have essentially the same shape. It's just going to be the reflection of that shape. So let's see here. For y equal to log base b of x. My b looks terrible there. I will say your base can be any positive number that's not 1. So just like before, our base has to be positive and not equal to 1. I will also point out that for logarithms especially, we usually don't pick bases between 0 and 1. We can, and if we have time, I'll show you one, but usually our base is just bigger than 1. So for logarithms like this, we have a graph as follows. You're going to have a x-intercept at 1, 0, because if x is 1, b to what power equals 1? What power does it have to be?
0.
Exactly. So just like how with the exponential graph, you always get a y-intercept of 0, 1. For a logarithmic graph, you always get an x-intercept of 1, 0. And then it's going to have this shape. And we have a vertical asymptote at x equal to 0. And oftentimes, we will also plot the point b 1 comma b. B comma 1, sorry. You don't have to plot another point, as far as I'm concerned, but right, if we plug in b, log base b of b, that's a different thing. Log base b of b is equal to 1. Because b to the first power equals b. Okay. A couple things I want to say about this. The domain of this function, if you haven't shifted it left or right, is positive real numbers. And the range of this function is all real numbers. And the reason I'm really mentioning this is because I want to show you that it's exactly the stuff that's true for the exponential functions, except all the x and y things have switched places. So over here in a different color, let me just show you here's y equal to b to the x. Looks like this. Has a y-intercept of 0, 1, and also has the point 1, comma b. And if we look at this one, the domain is everything. It's all real numbers. So the domain here is the same as the range over there. And the range here is all positive numbers from 0 to infinity. The range here is the same as the domain over there. And what else? This point here is the, right, these points are just these points with the x and y values interchanged. And lastly, the horizontal asymptote here is y equals 0, which is what you get if you take the vertical asymptote x equals 0 and interchange x and y. So everything here is just everything there with x and y changing places. And that is always a true thing about inverse functions, that you always have this x and y changing. In fact, I'm sure for a lot of you that makes a lot of sense, right? Because you know that the way you find an inverse function is you interchange x and y, and then you solve for y. So that's not without good reason, right? They're inverse functions exactly because of that. Let's see, what do I got here? I'm in the way. So so before we go further, I just want to show you, because I did do some graphing on Desmos. Let me share my screen.
So the log graph is basically y equals b of x mirrored across the origin?
Well, I wouldn't say mirrored across the origin. I would say mirrored across the line y equals x, which is actually exactly what I'm about to show you. But that's a very good observation. Typically, so if someone said mirrored across the origin, they would probably, usually that means like a rotational kind of symmetry. Like we would all say that the function y equals x cubed is symmetric about the origin. But yeah, so let me show you what I mean. So here's y equals 2 to the x. Here's y equals log base 2 of x. And then here's the line that they're mirrored in, y equals x. So you can see, oh yeah, there's exactly this kind of mirroring. In fact, here we can see some of the mirrors because I graphed some lines to help us do that. That's right, so this point here, let me zoom in a little bit. So this point here, 2, 1, and this point here, 1, 2, right? They're exactly mirrored. Why don't you stay clicked? There we go, yeah. Are exactly mirrored across the point there, right? They just interchange x and y. And the same for this one here, right? These points are just mirrored. And these, whoops, let me zoom in. And these points even. So they're definitely mirrored across this line. There's definitely an intersection of a 90-degree angle there. And there was something else I wanted to say. Oh, and I should say, it makes sense when you think about it for a little bit that if you're interchanging the x and y values, you're exactly reflecting across the line y equals x and getting that swap when you go across the line like that. So hopefully that seems relatively clear, maybe not clear, but at least worthwhile. So yes, our exponential graph and our logarithmic graph are always going to look like these mirrors of each other. In fact, we could totally, I mean, I just had it on there, but you could also draw it right here, right? This one's going to look exactly like that. And they're exactly, right? They're exactly crossing each other like that. I mean, my drawing is not perfect. Desmos was much better for this than my drawing. So that's kind of the idea. Logarithms, exponentials, very closely related to each other. They are inverse functions, just like trig functions and their inverse functions are inverse functions. Now, the trig function, inverse function names are literally inverse sine. This name we don't call, right? We don't call this, right? We don't call this inverse b to the x. We call it log base b of x. But it's the same idea. It is the inverse of b to the x. Just like this 2 to the x, this log base 2 of x is the inverse of 2 to the x because all the x and y's are just switching places. Okay, so enough about that. Well, not enough about that. So now what we're going to do is we're mostly just going to graph some logarithms. But I really, really, really want you to remember, have it stick in your head, that when you're finding a logarithm, if you're finding a logarithm, you're just finding the power that you raise the base to get the answer. So just for one more quick example, maybe two more quick examples, log base 6 of 36 would be equal to what? You can show me on your fingers, you can write it in the chat. There's one wrong answer and there's one right answer that I expect to get. One of those is wrong and one of those is right. Is it 6 or is it 2? That's right. Definitely 2, because 6 to the second power is equal to 36. But sometimes people want to write 6 because 6 times 6 is 36. So be careful, right? You're not looking for what you multiply by, you're looking for the power you raise it to. In a similar way, you could say that log base 4 of 1/16 is equal to -2, because 4 to the negative second power is 1/4 squared, which is 1/16. So just try to remember, if you're finding what a logarithm is equal to, you're looking for the power or the exponent, that you raise this base to get this answer. People often draw this little picture like this, where they circle the base, and then they draw an arrow pointing to the power you raise it to, and then an arrow to the answer it's equal to, so that 6 to the second equals 36. So hopefully that's mildly helpful. All right, I got 20 minutes to do some graphing. Let's do it. Where is this? So the rest of this should be not too terrible in that it's supposed to be just like the exponential graphs, pretty, I want you to be pretty not very detailed is the words I'm trying. There's got to be a better way to say not very detailed. You don't have to be super detailed. So if I was going to say graph like y equals log base 3 of x, that's a 3, not an 8. Here's what I really want. I want your x-intercept at 1, 0. I want your vertical asymptote at x equals 0, and then it's got to have the right shape. I mean, I should label this point 1, 0, and that's enough. If you really, really want another point, and I understand wanting another point, you can go over here, and really it doesn't have to be precise, and be like, okay, I know this point would be 3, 1. Because if I plug in 3 for x, log base 3 of 3, or 3 to what power equals 3, should be 1. If you really want even one more point, you can go over here to 1/3, -1. Often in a lot of textbooks, you will see these two other easy points to graph, right? And usually it's the point that gives you 1 as a y value and -1 as a y value. And that's, I think, all I want. Yeah. Something else I want to say here? Or no? So before we graph more, I just want to point out, so usually in a live classroom where I could talk to a person and maybe show people their hands, I would walk around and ask someone for a hand that is better looking than mine. So everyone can show their hands if they want. But I've got, so the way I usually think about this is this graph, your right hand. Make sure it's your right hand. So this here is looking like 2 to the x. And this here, mine's not very good, is looking like log base 2 of x. So I'm going to go, let's see here for a second. I'm going to go to the gallery. I see a people. I'm going to go on Lindsay for a sec. Lindsay, I'm going to pin you. Let's see. Oh, yeah, that's great. So here's Lindsay's hand here. I don't know. Like there's a log base 2 of x, there's an e to the x. That's so good. Andrew, I want to see your hand too. Andrew, you're next. Let's see, how do I pin your video? Andrew, your logarithm looks good. Your 2 to the x is harder to see. You've got a really strong horizontal line there, which is kind of interesting. But yeah, all right. Enough bothering you guys about looking at your hands. But anyway, so what I used to tell students is that during a test, you can just look at your right hand and be like, oh, there's 2 to the x, or there's log base 2 of x. Or what I usually say is there's e to the x, and there's the natural log of x. On your right hand, it's gotta be your right hand. But if you're at home, you could also just literally look at Desmos and say, oh yeah, there's e. So maybe not super useful in the current times, but still it's on your right hand. Do make sure though, especially if you're right-handed and you're writing while you're taking a test, don't look at your left hand. That's gonna be not the functions you want. That's gonna be e to the negative x and natural log of negative x, right? So that's not as helpful. All right, but let's graph a few more. Okay, but really graphing most of these is just, I want it to be like 2 steps. So if I was graphing y equal to log base 5 of x. Okay, I know it's a logarithm. I know it's got the usual shape. I know it's going to pass to the point. Really, I'm not even going to draw this point until I'm just going to draw the logarithm first. So I'm going to try and draw it so it has a vertical asymptote. As I start down here, I should keep moving to the right. And that point's 1, 0. A couple things when you're drawing these, they should always look like they keep getting bigger, right? There's never it never like turns around like that. There's no maxing out. It always just continues. So we draw an arrow to the right and kind of pointing upwards. So it keeps looking like it's getting bigger that way. And this arrow going down and slightly to the left. That's it. And if you wanted, you could throw another point on there, like 5, 1. Or 25, right? Way out here, you could do 25, 2, but you don't want that, right? That's more than we're looking for. So you should probably label the vertical asymptote, even though if you've drawn it correctly, it's pretty obvious what it is. The vertical asymptote here is x equal to 0. Let's see. Yeah, we can talk about this. So, yeah. Okay. So you can have a logarithm with a fractional base. It's just weird and we don't really do it. So you're never, I don't want to say never, you are almost never going to have anyone ask you to graph something like log base 1/2 of x. Because really, well, one, it's dumb, but more importantly, really, it's that there's a better way to write it. So in fact, it's very similar to like how you can write 1/2 to the x is really the same as 2 to the negative x. There's a similar, but not quite the same way of rewriting this. So let's take a look at what it looks like. So if I was going to do this, I'm actually going to plot some points here. Yeah. So let's just think for a minute. I'm going to pick values of x that are nice powers of 1/2. So I'm going to pick values of x like 1/8 or 1/4 or 1/2 or 1 or 2 or 4. So when I say log base 1/2 of 1/8, the answer or the value is 3 because 1/2 to the 3rd power is equal to 1/8. And log base 1/2 of 1/4 is equal to 2 because 1/2 to the 2nd is equal to 1/4. And log base 1/2 of 1/2 is equal to 1 because 1/2 to the 1 is equal to 1/2. And then Running out of room here. Log base 1/2 of 1 is 0. Log any base of 1 is equal to 0, just like anything to the 0th power is equal to 1. And finally, a couple interesting ones. Log base 1/2 of 2 is equal to -1, because 1/2 to the negative first power is just the reciprocal, which is 2, which is what we want. And lastly, 4, log base 1/2 of 4 is -2, because 1/2 to the negative second power is equal to +4. Okay. So here's what this graph looks like. So let's see, I'm going to start here. I've got the point 4, -2. I've got the point 2, -1. I've got 1, 0. I've got 1/2, 1. I've got 1/4, 2. And then I'm not going to plot that one. So it looks like it's doing this kind of deal. So it actually looks like I took the regular logarithmic function and flipped it over. So that you can also say that instead of being log base 1/2 of x, which is a perfectly legitimate thing to write, most people prefer to write it as negative log base 2 of x. I don't want you to worry about this. I just wanted to show it to you because no one's ever going to ask you for a weird base with a logarithm. It just doesn't happen. But if someone does, this is what you can do to fix it. So you can always take the reciprocal of this and change the sign here. So not that everyone's ever going to ask you to, but if I said, you know, I want to graph log base 2/3 of x, I would immediately say, okay, that's 2/3 is still a dumb number. It's negative log base 3/2 of x. Not super helpful, but still at least the base is greater than 1. And that's going to have this kind of shape. All right. Enough of that. Yeah. It's hot in here. It looks like the apocalypse outside, by the way, in Woodland. It's super smoky, as I imagine it is for many of you in many parts of California. But it's also really, really windy. So it just looks like a hurricane. No, it looks like not a hurricane, a tornado. It looks kind of like a tornado. I mean, it doesn't look like a tornado, but it looks like the setting in a movie where they're like, a tornado's coming. It's not a tornado, but it kind of just feels like it looks kind of gross out there. And like, you wouldn't be surprised if there was a tornado on the horizon. There isn't. Although there was a tornado here like a year ago, like a really small one, but there was totally a tornado like less than a mile from my house, which was kind of cool and kind of scary. It was a small tornado. It wasn't like a scary tornado. Anyway, Google it. If you Google like Woodland tornado, I bet you can find a video of it. Okay, a couple other things. One other base we like to talk about, base we've already talked about, is E, which is approximately 2.7. So just like we like to graph y equals e to the x, which looks like this. Right, it has the points 0, 1, and 1e. We can also graph y equal to log base e of x, which has the usual logarithmic shape. 1, 0, e comma 1. Now, the reason I mention this one specifically is because the log base e logarithm comes up so frequently. Right? It's the natural base. This is called the natural logarithm, that we often abbreviate it as the natural log of x. So that we don't write the base. Everyone knows that when you write ln, what you really mean is log base e. So don't get confused by this. It's not anything tricky. It's literally just an abbreviation. It's actually the same kind of thing right? The other really important number that comes up a lot for logarithms is base 10, because we're kind of a base 10 society. It's in the same way that we abbreviate log base 10 of x as just log of x. So those are just abbreviations. Don't be scared by them. When you see this, you should be like, oh, the base is 10. When you see this, you should be like, oh, the base is e. Nothing to be afraid of. Okay. Cool. So the last thing I want to talk about graphing wise is just shifting these things. And although you can shift them up, down, left, right, you could stretch them, you could also smush them, and you can reflect them. The only one I really want to talk about today is shifting left and right, because that's the thing that kind of has the most noticeable change right away. Don't worry, there's no tornadoes out there. At least not in my neck of the woods. So with the exponential graphs, we shifted up and down. And the way you shift up and down is by adding or subtracting on the outside of the function. To shift left and right, you add or subtract on the inside of the function. So I want to look at something like y equal to log base 5 of x minus 3. And here's the thing I want to think about. So before, right? So before that, I'm actually first going to do y equals log base 5 of x. So log base 5 of x just looks like this. 0.10. So I know that when I plug in 1 for x, log base 5 of 1, 5 to what power equals 1 is equal to 0. And I get the 0.10. But now, when I subtract 3 here, x has to be 3 larger. So instead of getting the 0.10, x now has to be 4, so that y is equal to 0. So everything has to be 3 bigger, which means we shift 3 to the right. Specifically, my vertical asymptote is now at x equal to 3. And my x-intercept is 3 bigger than it was over here at 4. I didn't really leave myself enough room to draw the graph nicely, but that's what we've got. Everything moved 3 to the right. So the vertical asymptote is 0 plus 3, which is 3, and the x-intercept is 1 plus 3, which is 4. And that's, again, that's kind of it, right? You shift to the right, you don't have to do much. Let's look at one more to the right. Let's see here. Sure. Let's look at this one. Let's look at y equal to log of x minus 2. So this is going to shift 2 to the right. The way I kind of think about these logarithms is my vertical asymptote is going to live at whatever value of x makes the inside of the logarithm equal to 0. So usually it's at 0 if we haven't moved it left or right. But here, it's going to be at x equal to 2, because 2 minus 2 is 0. Or in the previous one, right, it's going to be at x equal to 3, because 3 minus 3 is equal to 0. So my vertical asymptote is going to be at x equals 2. And my intercept is going to be 1 more after that. It's going to be at x equal to 3. What's my base here?
10.
Yeah, 10. So if you wanted to throw one more point in there, you could throw in the point 12 comma 1, right? It would usually be 10 comma 1, but then we're shifting it 2 to the right to get 12 comma 1. And it makes sense. You plug in 12, 12 minus 2 is 10, and log of 10 is log base 10 of 10, which is just 1. Right? Log of 12 minus 2 is log of 10. Just log of 10 of 10. Okay. I'll do one. I really want to do like 3 more examples, but I will try to limit myself to 1 or maybe 2. I know it's 217. So shifting to the left adds a complication. So I'm going to graph log base 3 of x plus 9. So I know it's going to shift it 9 to the left. Which means my new vertical asymptote, instead of being 0, my vertical asymptote is going to be x equal to 0 minus 9. I'm literally just subtracting 9 from everything. So if my old vertical asymptote was 0, my new vertical asymptote is 0 minus 9. And my new x-intercept, it would have been 1, but now it's 1 minus 9, which is negative 8. So negative 8, 0. And I'll try to be, so I'm not always super precise like this. So here's my vertical asymptote, and oosh, that's a negative 9, believe it or not. Here's my x-intercept at negative 8. And, okay, sure. That's kind of what it looks like. And the thing that you might have noticed that we also have to deal with is that we have a y-intercept. So let me ask you guys, how do we usually find the y-intercept? What's the thing we always do if we're trying to find the y-intercept?
We said
Factor?
Factoring is a good answer, but not for this one, but you're not wrong. We often factor, but someone else was saying we set something.
we set x to 0.
Exactly. That is always the thing we do for finding the y-intercept. We set x equal to 0. So if I set x equal to 0, then y is going to equal log base 3 of 0 plus 9. So that's just log base 3 of 9. And what's that? What is log base 3 of 9? Or 3 to what power is equal to 9?
Second?
Yeah, exactly. So this point here is 0 comma 2. So when you shift to the left, there's also going to be a y-intercept, and the way you're going to find it is by setting x equal to 0. And sometimes it's not quite as nice as this. So I know it's 220. Let me throw up one more quick example. Something I'm saying I'm going to vomit. No, let me put one more example on the board, not throw up one more example, just so I can show you very quickly. Don't worry, this will just take a second. I really promise. Here's one more example that'll be very fast. Y equal to log base 8 of x plus 4. Okay, yeah. Yeah, exactly. So I was trying to stop from happening. So left 4, so here we go. So the vertical asymptote is at x equal to negative 4. The x-intercept is going to be at negative 3. Because again, I've just shifted everything left by 4. I know my xy scale is not good, that's fine. Usually we'd have the point 8 comma 1, but if we shift that left by 4, we really have the point 4 comma 1, which again makes sense, right? If we plug in 4, 4 plus 4 is 8, and log base 8 of 8 is 1. So we should get the point 4, 1. All right, my y-intercept here is a little more challenging. If I set x equal to 0 for my y-intercept, I get y equal to log base 8 of 4. And this is where people have a tough time, because log base 8 of 4 is not 1/2. I know people, even if you don't want to admit it, I know people want to say it's 1/2, because 8 times 1/2 is equal to 4. But that's not what we're looking for. We're really looking for 8 to what power equals 4. So that's actually what we're going to do. We're just going to rewrite this. I'm going to use y instead of a question mark. 8 to the y is equal to 4. And then we're going to do, so this only is really doable when you have bases that have a common base, right? 8 and 4 are both commonly powers of 2. So I'm going to rewrite 8 as 2 to the 3rd to the y. I'm going to write 4 as 2 squared. And then 2 to the 3rd to the y becomes 2 to the 3y equal to 2 squared. And then if the bases are the same, the powers have to be the same. So 3y equals 2 and y equals 2/3. So that's what this y-intercept here is. It's 0, 2/3. And if this was log base 7 of x plus 4, you couldn't do this, right? You couldn't be like 7 to the y equals 4. We can't solve that nicely. But if they are both powers of the same number, like you have an 8 and a 4, or a 9 and a 3, or some other things that have a base in common, then you can totally solve this sort of equation. So